name is Dr. Sarah Speight, and I'm a postdoc at Memorial University. I'm working with Steve Piercy and Jacob Hanley, and today I'm presenting results and sort of a summary of our chapter work for the synthesis. And so I've also got information related to Priyal Daya's thesis. She's a PhD thesis at St. Mary's University with Jake Hanley, and so we'll see some of her melt inclusion results today. So looking at just generally for an idea of the project and what our goals were as far as my work is concerned, we're looking at the VMS thematic project. So we've all been kind of clustered together, so Taos and Keaton, and looking at that. We've got, for my work, specifically focusing on felsic volcanics and plutonic rocks in the Abitibi. So here I've highlighted, so this is the Superior Province, but highlighting with the red box, just the location in the Abitibi, as well as kind of beyond the Abitibi, because I do have samples that we're comparing in the Eastern Geraldton transect, as well as looking at other samples from the Wawa, and just kind of wanting to expand a little bit beyond the Abitibi. And so we'll be looking at zircon mineral chemistry, and I'm using tracer isotopes and geochronology data to look at how the role of magmatism with respect to VMS endowment, and generally trying to characterize whether or not we can see signatures related to endowment in the zircon mineral chemistry or in the zircon-hosted melt inclusions that Priyal's working on. So to give an idea of the analytical workflow that we've got for both of these projects, with the zircons, we are looking at doing very much a stepwise analytical workflow. So starting at looking at a large amount of imaging, and I'll show CL images here in a moment. But SEM, BSE, CL imaging at Memorial University, along with then corresponding electron microprobe analysis of the zircons. For my work, I put a really big emphasis on obtaining core zircon data, which is different from the rim zircon data. And in my database, which will be available as the project finishes up and be part of the Metal Earth databases, those analyses are marked as such, so that when you're looking at either an age distribution, you can know if you're looking at zircon core data, if you're looking at final emplacement magmatic characteristics, you're going to want to ask a different question and look at the zircon rim data. So depending on the question you're asking, you're going to look at this database a little bit differently. And that's kind of one of the things I'm going to show today, and because we're looking at it, today I'll show you the sort of spatial perspective. And so finally then, after we have the electron microprobe analyses, we use that to do internal standardization of the laser ablation work. So we collect uranium, lead, and trace elements concurrently. Then from those analyses, we go and look at the laser ablation for lutetium hafnium isotopes. So with that, we do a bit of a step up as far as the ablation pit goes. The ablation pits for uranium, lead, and trace elements are about 20 micron that we use, and then we expand that to 100, I think it was 100 microns for the lutetium hafnium. So it gives us a better area to look at those, and we overlap that, and I'll show that actually right here. So this is some of the CL images of zircons, and I'll just skip ahead to show. We do the laser ablation. Here's an example where you can see laser ablation is these orange circles, and then the larger purple circles mark where we would do laser ablation for lutetium hafnium. And then you can see these orange circles here are marking microprobe analyses. So these are done in a way that we can layer the data together so that we can have a really robust data set, and when we start comparing things, we can be confident in the differences that we see in core and rim chemistry. And I'll just go back a sec. Just to note the samples that we're looking at for the zircon analysis. So I've picked 74 samples from across the Abitibi, and then Priyal's work, which is looking at the melt inclusions, and they also have done the same kind of CL imaging, electron microprobe analysis for internal standardization, and then moving through to uranium trace elements when possible, and then laser ablation of the melt inclusions as a whole, because as we know we need to analyze the whole thing in order to obtain the full chemistry of the inclusion. But for hers, her focus is more on a district scale. So she's looking at Kid Creek and at Doyon-Biscay-Laurent for her more smaller set, which is about 15 samples. So to give an idea of where specifically we're looking, this is an image I pulled from the compilation that was done by Jack and the Abitibi, the geophysics work, and I like it a lot because it lays out where these transects are located. As I mentioned, my samples generally are from the Abitibi, but I do also have samples from the Wabigoon transect, and looking sort of towards the edge of the Western Superior. And to kind of zoom in on that a bit, because I wanted to color code these transects since I'm going to be comparing them in the next couple slides. So for the rest of my data, you can kind of keep this color scheme in mind. As we've gone, I ended up going from east to west, looking at Chibougamau, Malartic, Rouyn-Noranda, Larder Lake here is in orange. Cobalt is not actually necessarily more westerly than Noranda, but I had to make it a different color anyways, so it turns out to be yellow. So we have these warmer colors on the eastern side of the Abitibi, and then when we're looking at the data in the next couple slides, the cooler colors as we keep going west, we've got Matheson, as well as Timmins, Swayze, and then Geraldton in purple. So this kind of, again, east to west look at the color scheme, we can see you can carry that through in the next few slides. So to jump into some of the data itself, we're looking here at epsilon hafnium calculated from my Zircon analyses. These are looking at, so here we have epsilon hafnium on the right. I've plotted these now because I'm looking at the spatial perspective of this and the Zircon mineral chemistry. This is plotted using the longitude. So again, that color scheme, red being in the eastern side of the Abitibi and then moving to the west towards the purple side, we have that change across the transects. So at first, there's obviously a lot of different data, and I do have these also separated. The symbology here is the open symbols are all of my felsic volcanics samples. So that would be the rhyolites, the felsic tuffs, crystal tuffs, anything classified as the felsic volcanics are put together that way. And then the filled samples, the squares, diamonds, and circles are the intrusions that I have for my set. So I've got felsic intrusions and intermediate intrusions. There's one mafic intrusion that's in my sample set for comparison for the time being. But what I was interested in, because we are looking at this right now at more of a tectonic and province scale, we have to consider the data in that way. So instead of looking at maybe a sample, an individual Zircon scale, so this box here is showing the mean is about 4 epsilon hafnium for all this data across the Abitibi. And then so plus or minus 1 standard deviation, it gives you this range across all. Because as we've been kind of talking about, I think today in a few different talks, is that a lot of these things are happening at the same time. So I do expect to see Zircon with a 4 epsilon hafnium in one transect, and then I could find Zircon with that same signature in another. For me, the areas where I see significantly like higher, or maybe a pull up in higher epsilon hafnium values, or outliers where I start to see a pull down in epsilon hafnium, is where I can then go another stage and consider the tectonics and processes that are changing that signature there. And to be a little more conservative, I also did 2 standard deviations out to see what's captured there. So when I go back to 1, we see a little pull up in Chibougamau. We see some higher values, a lot actually over here at Noranda, a little as well in cobalt, and in the Timmins region, as well as a bit of pull up here up towards values of 8 epsilon hafnium in the eastern Wabigoon, which is different. The outliers down here we have a bit of cobalt and again Geraldton that are pulling down, as well as significantly is the Swayze. So the Swayze has the lowest epsilon hafnium values that I found in the data. And so looking at what that reflects as far as processes go is we have potential for crustal assimilation that is pulling these values down, and the potential for juvenile melt that's being added and pulling these values up in the Noranda region, which it's, again, kind of confirmation, but in another way. Even at the zircon mineral chemistry scale, we can see these processes that we've been talking about reflected. And if we look at, I also looked at the the depleted mantle, TDM, versus the crystallization age. So this is looking at this change in time in millions of years, again, versus looking east to west from Chibougamau to Geraldton. And the calculation here is just looking at the TDM, so the depleted mantle, calculated depleted mantle age, which all these were done using the published TIMS ages, and comparing it to that crystallization age, that published TIMS age. And when we look at that, it's kind of the flip side, because what they're starting to show us is when we have potentially crustal residency or assimilation. So ends up being the opposite, but generally a change of anything in this is highlighting around 0, sorry. And I've highlighted 50 million years in either direction because we would expect to see an older TDM compared to the crystallization age. The TDM is reflecting melt extraction and then progression, fractionation, and crystallization towards that crystallization age, the TIMS age that we get. So large differences between, in the positive direction, are showing that we have a much older TDM that's pulling that up here. And so we're seeing that as potentially crustal assimilation or thickened crust in the Swayze, which is the opposite, and even still conservatively looking at a 100 million year span. Noranda still pops out as having outliers, as well as Geraldton, and that then is looking at juvenile melt and that rifting that we've been talking about today. So, we did not plan this, but it turns out that the VMS group is very much considering the metal ocean perspective and trying to, I don't think it's piggybacking necessarily so much as synthesizing our data with what they're seeing in the metal ocean perspective. And so this is showing, again, we've seen it today a few times, Chris's map, just a blown up version of looking at the Moho depth. So again, the cooler areas, and they've got these marked off with the interpreted rift regions, which I'm very excited for Aaron's new one that has the named rifts and microplates. I think that's very cool. So looking at this with respect to then my zircon mineral chemistry data, my question was, from a modern ocean perspective and rifts and juvenile crust signatures that we can see plainly here in these rifted regions, compared to more thick areas of crust where we have the warmer regions, thicker depths to Moho in this, do I see corresponding signatures in the zircon data? So the answer is yes. And I'm gonna be able to just kind of highlight in some of these regions. So you'll have to forgive the quality. I wanted this to be very big for the presentation, but one downside I will say to using the zircon mineral chemistry data, which on a sample scale we can get an abundant amount of data, but when we plot it spatially, it does come down to one GPS coordinate. So an artifact of that is that we do have a lot of stacking of the symbols in this case. So it's something that I'll work on as far as displaying the data in different ways. But what I've plotted our epsilon hafnium data as, so really high values, so those high outliers, such as Noranda, have the yellow circle symbols, and the lower ones where we had lower epsilon hafnium values, we had the Swayze, and that's in the blue circles. So and also that would be potentially thicker crust. So when we compare that to this Moho map, the color scheme is actually opposite. So I would expect to see, my yellow circles on regions where we have the blue crust, because that's where we have juvenile input, or in this case also a lot of the green. So here we have my zircon samples, and this is one here. There's not that many outliers as I showed, but we do have one here, and this is part of the Noranda-Larder Lake district. And interestingly enough, there is another one is following in more the Geraldton region. And if I understand it correctly, the Western Superior Moho maps might be in the works. So I am very excited to do future comparisons with my other samples to see how they plot. But just to then compare, I wanted to then plot where I've marked these regions that show that juvenile input, and it does very much overlap and correspond with the rifted zones that the Metal Ocean group has interpreted. So I think there's a strong correlation between what we see in the modern ocean and the tectonic architecture compared to what we're seeing even down to the mineral chemistry scale in the Abitibi. And just to, as another kind of point towards that, looking at different types of mineral chemistry, I've shown this figure before, looking at gadolinium over ytterbium versus delta FMQ. That was also something I found interesting listening to Kieran's talk, is that their assemblages, I saw values of plus delta FMQ +1, +2, but we actually, or when I was looking at mine, my well-endowed samples all have delta FMQs of +3 or higher. So we've been considering in our work that oxygen fugacity is playing a large role in VMS mineralization and well-endowed regions, and it seems to be something that's staying consistent in other work. But talking to Pierre Simon and looking at some of the whole rock signatures and this ytterbium that they've been discussing, and I'm looking here at gadolinium over ytterbium, initially considering that this might be reflecting thicker crust and thinner, but it's also been found in their work to represent potentially signs of partial melting or crustal residence, these elevated gadolinium ytterbium values. And a lot of these are the intermediate intrusions. So it's another facet kind of that I'm going to try to be able to pull apart, is whether or not we have partial melting crustal residence versus like how I can split this data up more to look at the endowment and how they relate. And as I mentioned, I have a few slides from Prial's work, so we're kind of switching over into the melt inclusion realm now. So these are Zircon-hosted melt inclusions that she's working with, and for her thesis, she's looking at, like I mentioned, 2 different deposits, looking at well-endowed VMS deposits from Doyon, Bousquet-Larande, and Lorraine Penna, as well as looking at Kid Creek. So these are both, she's using them to consider gold-rich VMS compared to gold-poor. And today, because her final chapter is focusing on Kid Creek, that's what her slides are going to be looking at. And for her thesis, she's looking to defend at the end of this term and get papers submitted for the summer. So for her data, this is looking at sodium plus potassium, so it's total alkali diagram versus silica. And there's 2 types of data shown on here. She has this gray field, which is looking at the bulk rock data from Kid Creek, and then plotted on top of that are her silicate melt inclusion data. So this is, she's done a lot of work to do a lot of data reduction, which I'll let everybody find out from her thesis about. But what she's able to do then is to calculate and obtain essentially comparison to the whole rock data in the melt inclusions. So when we plot them together, we would expect to see either very similar melt inclusion chemistry to the whole rock or slightly of a change. And what she does find that there's overlap in her silicate melt inclusion data with a bit of a pull to higher silicate directions. And she's considering that to be high silica from contamination, from quartz contamination in the melt inclusion data. But from looking at compositions of silicate melt inclusions hosted in the footwall rhyolites, she's looking at fragmental rhyolites and the hanging wall rhyolites. And she found that the melt inclusion chemistry overlap in all cases. So whether she was looking at, in her stratigraphic package, if she was looking at the footwall, the fragmental, or the hanging wall, all the chemistry all overlap in this case as far as the bulk goes. But then she gets into looking at the metals next. So looking at, again, so this is Kid Creek data, more gold-poor VMS to compare with her other region. So she's looking at, here we've got plotting copper in ppm, zinc, and lead. So these are all metal values from her melt inclusions. So the melt inclusion, and to give a small perspective, I should have at the beginning, the melt inclusion data is essentially reflecting early primary melts captured as the zircons grew. So the idea being that they reflect and should have a more or less fractionated chemistry, and they should give us an idea of primary magmatic conditions in this VMS setting. So with respect to then looking at footwall, the fragmental rhyolite, and the hanging wall, so you're moving up stratigraphy in this direction, copper values decrease, as well as zinc. And then the lead values tend to stay somewhat similar. But what they've interpreted this to mean, at least seeing this decrease going from footwall to hanging wall, is that at some point these magmas may have degassed and released metals so that the melt chemistry, by the time it was entrapped as part of the hanging wall sequence, the metals aren't as present as they were when the footwall rhyolites were depositing. So part of that metallogenic history is being recorded in the melt inclusion data here. And Priyal will be looking at incorporating a lot of those conclusions in our chapter. Okay. And so finally, I'll just, for the real highlight here, looking at the melt inclusion data is, this is the zircons that host the melt inclusions now. So because it's a bit of a dual study where you get zircon mineral chemistry at the same time as you're getting the melt inclusion chemistry. So here they calculated FO2 compared to temperature, to temperature in zircon, and what they found in Kid Creek is different actually than in her last presentation where she showed FO2. Here we have changes FO2 kind of decreasing from the footwall rhyolites down and to the hanging wall rhyolites. So a shift towards lower temperatures and a decrease in FO2. And then we also, this is now our gold pour VMS system. We saw in the Hebecore and looking at the Doyon-Bousquet data, we actually saw the opposite where we had decreasing temperatures and then we ended up with a change where we had increasing FO2 in the end. And it's where we have that gold-rich environment. So there was changes recorded in that data as well. So to summarize kind of briefly then, the epsilon hafnium signatures for zircon in the Swayze transect, they show that pull down feature and those lower epsilon hafnium values compared to the remaining transects. I think that's a really important thing to take away is that in this comparison, in this region, when we're looking at for outliers to determine what might have affected those in those processes, it's going to be, I think, a little case dependent. So this suggests that at least in the Swayze region where we have those lower values, the crustal assimilation or longer residence times were potentially occurring here. And on the MOHO map, that region also showed a deeper depth MOHO. So the thickened crust, the crustal assimilation, a lack of VMS deposits potentially is part of this reason why Swayze is less endowed in VMS. And it's what we're seeing in our zircon mineral chemistry data and seems to be carrying through many of the other studies. Which is then different from Noranda, where we had those very notable elevated epsilon hafnium values and that pull-up feature, which is suggesting the addition of juvenile magma. And it is looking like one of the largest rifted centers in the MOHO and the interpreted maps. So I think it is another corroboration that this interpretation is moving in the right direction, I think, especially since this was a very independent comparison. And then for the melt inclusion data, we have the gold-rich versus gold-poor Kid Creek comparison that Priyal is doing and will be synthesized as part of our chapter. What's coming out is that the gold-rich VMS deposits have really oxidized signatures, and that seems to be a really important feature in creating well-endowed VMS regions. We see that mirrored in the zircon mineral chemistry as well. The oxygen fugacity, like I'm mentioning, is playing a really big part. And they also are finding, because they did extensive TIMS dating, that these shifts in FO2 happen over a very short period of time. So that's another aspect, the time aspect, to be considered here. And notably, for those oxidizing conditions in the zircon chemistry, I've shown it before, but I'll just noting it here that I found increasing oxidizing conditions specifically in Deloro, Kid Monroe, and Blake River assemblages. So these being the most fertile that in our sequence that we're comparing with. So I think it's really important. And we have some limitations in the study, but you can read the paper for that. So thank you very much.